Hola! Welcome to Absolute Value and Reciprocal for Pre-Calculus of Math 11. Today we're taking a look at absolute value functions, which is section 8.1. You know what, this section, pretty straightforward. It really has to do with going back and graphing again. Graphing lines, graphing parabolas. So the equation of an absolute value function has the form y equals absolute f of x. So you can see here these two little vertical lines that encompass our function f of x make it an absolute value. So f of x is the function, we're taking the absolute value of that function. The x-intercept of the graph of y equals absolute f of x is called a critical point. Why is it a critical point? Well, it's because critical changes occur there. Because some critical change occurs to the graph at this point. Recall that the absolute value function will take any negative value and make it positive. So if you think about just absolute values of numbers, like the absolute value of -2 is 2. The absolute value of 7, well, since it's already positive, it remains positive. The absolute value of 0, that's also 0. So absolute value takes any negative value and makes it positive. That's basically the only thing it does. So when we talk about graphing an absolute value function, like y equals absolute of 2/3 x minus 2, we need to consider first the graph of the function if it didn't have absolute values. So what I want to do is I want to graph, let me do this in kind of like a lighter color. I want to graph what's inside the absolute value sign. So for this case, we have y equals 2/3 x minus 2. That is a linear equation. We have a slope of 2/3, so a rise of 2 for a run of 3. And we have a y-intercept of -2. So let's draw just a pretty quick line with y equals 2/3 x minus 2. So we cross at -2, rise 2, run 3, rise 2, run 3. And we can start seeing this shape, which is a line, kind of manifest itself there. So there's our y equals 2/3 x minus 2. So what does absolute value do? Well, absolute value takes anything that's negative and makes it positive. And for our purposes, any negative y values become positive. What does that look like on our picture is anything that's negative, anything that's below the x-axis gets reflected up. Anything that's currently above the x-axis just stays there. So in this region here, we have that the y values are positive. Here y is 0, here's y's 1, here's y's 2, etc., etc., etc. Because it's all above the x-axis, that just stays on our curve. That's perfectly fine. The stuff that's below gets mirrored above. So that y-intercept of -2 becomes a y-intercept of +2. This point here, which is -3, -4, becomes -3, +4. And if we connect the dots, we get basically something that looks like a V. A lot of people will call it the V function. But really, it has to do with taking a piece of the curve, which is below the axis, and reflect that piece above. So now we can answer some of the other questions here. Identify the intercepts. Well, I see an x-intercept, or x0, of x equals 3. That's basically where it touches or crosses the x-axis. I can just pick off a y-intercept, and it looks like y equals 2 is the y-intercept. Domain and range, so let's maybe write a domain statement. X, given that x is a member of, well, I think we get all real values here. Let's try a range. It looks like, for our purposes, y, given that we have all the y values, which are greater than or equal to 0. So everything that's above 0, and including 0, because absolute value of 0 is still 0. So there's a domain and range statement for this absolute value graph, and there's the graph. So quick recap, graph the original function that's inside the absolute value signs, and then just take anything that's negative, anything below the x-axis, and reflect that piece up. So here I've gone with a parabola inside the absolute value signs. So let's first graph 2x plus 3 minus 2. Let's do that in light blue. Or actually, why don't you go ahead, give this a try, sketch this graph, see if you can come up with the absolute value. Hit pause now. So this is a graph which is shifted left 3 and down 2 because the vertex is -3, -2. The a value is 2, so it's expanded by 2. So out 1, up 2. 2 goes to 4, 5, 6, 7, 8. 2, 8. And we can draw maybe just again a nice kind of dotted light parabola in there. So that's what the parabola looks like without taking the absolute value. So now when we take the absolute value, what we're doing is anything that's below the curve, we reflect up. Anything that's below the x-axis or above the x-axis. Above the x-axis, I'm going to draw that in solid. That stuff remains the same there. And what happens is the stuff that's below this piece around the vertex gets reflected up. So it's kind of important to be able to do the curvature the same way. It curves out to those points. And there we go. That is a graph of, let me just kind of get rid of a little bit of that bottom piece. That black graph is a graph of that absolute value of that parabola. Picking off some x-intercepts, certainly here if the x-intercepts didn't work out to be very nice values, you'd have to probably solve this algebraically. I can tell that they are -4 and -2. The y-intercepts, or intercept in this case, a little bit tougher. It doesn't follow my graph, so why don't I do this algebraically? So what we're doing here is y is the absolute value of 2 times. The y-intercept occurs when x equals 0. So if I just plug 0 in and solve, I should be able to figure out what the y-intercept is. 3 squared is 9, so 2 times 9 minus 2. So that's 18 minus 2, absolute valued, and that's absolute value of 16. So lo and behold, that's 16. So we have a y value of 16 as our as our y-intercept. Domain and range again. You know what? It's not so tough with the domain. We're going to see a lot of x equals all reals. And for now, looks like the range is also everything greater than or equal to 0. So those two things so far haven't really changed that much. Now one of the problems that we have to do is how do we define an absolute value graph without using absolute value signs? So what we're going to take a look at here is you can use something called a piecewise function. Sometimes it's called a discontinuous function, but let's call it piecewise function, to describe a graph that has distinctly different graphs, so very obviously different pieces going on, and they're defined on different parts of x. So for example, if we graph y equals absolute x, let me just off to the side graph that. Y equals absolute x is, let's take a blue y equals x graph and reflect that up. Okay, so that piece there remains, and we have an absolute value graph heading up like that. So there's the absolute x graph. How do I know, or where is the breakpoint here? Where does this graph change? Well, it changes a lot at x equals 0. On the left-hand side of x equals 0, we have a line sloping up and left. On the right-hand side, we have a line sloping up and right. So that x equals 0 is really going to be our breakpoint. What we're going to do is we're going to write two different statements based on 0. So let's say we want all the x values that are less than 0, and let's say we want all the x values that are bigger than 0. So the two sides of 0. Now the problem here is that one of them we have to pick as equals. It doesn't matter which. You can put the line on whichever you want. I'll just stick it there. Let's talk about maybe x greater than or equal to 0 here. What does that graph really entail? That's basically just a y equals x graph. So all we need to do is write y equals x there. How about when x is less than 0 in this region here to the left of the y-axis? That looks like a negative x graph. So what I've done is I've broken up the function into two distinct functions. Negative x is a nice line with a y-intercept of 0, slope of -1, and positive x. So we should be able to do this for the same thing. So what I want you to do is I want you to take this y equals absolute -2x minus 6, hit pause, try and sketch the graph, and then I'll go through and show you what the piecewise function is. Hit pause now. So it has a y-intercept of -6, has a slope of -2. So I'm going to draw just a couple of dots here, rising 2, running -1, and the left piece certainly looks like that. And let me kind of maybe make this a little bit more dotted. And when I reflect that piece up, that intercept of -6 is my intercept of my new function here. And there's the second piece. So what do I want to do? I want to define my piecewise function f of x as, and if, where's the breakpoint? Where does stuff kind of go crazy here is at x equals -3. So let's make that the spot where we change stuff, when x is less than -3 and when x is greater than or equal to -3. Let's take a look here. It's actually the blue graph on the left-hand side, this black piece here. What does that look like? That looks like a regular old line with a y-intercept of -6 and a slope of -2. So that's really just that -2x minus 6 function. Great. What about the other curve? Well, how do I define this line is, again, based on slope and y-intercept. My y-intercept is 6, positive 6 in this case. And my slope is a rise of 2 for a run of 1, so 2x plus 6. Be a little bit careful. It's not simply every time just change all the negatives to positives if you can. That's not always the case, particularly when we talk about perhaps parabolas. So finally, let's take a look at this parabola. This parabola that we have here is not written in standard form, so we're going to have to complete the square on this, unfortunately. Let's pull out a negative sign and have a -8 just sitting off towards the side there. So completing the square, I want to leave everything inside the absolute value function. Half of the linear term is 3 squared is 9, so we're going to add 9 and subtract 9. So let's pull out that -9. -9 times the negative sign out front makes it +9, -8 outside. We can now complete the square, and that's x minus 3, perfectly squared. 9 minus 8 is +1. So there's a standard form equation. It's flipped upside down, it's shifted to the right 3, and up 1. So let me graph that. Again, let me go in kind of a nice blue here for that graph. This should be, again, kind of review. So I'm not going to dwell too much on how I graph this, certainly. Dotted line again. So anything above is going to remain there. So anything above the axis, this little piece near the vertex, that certainly stays there. The below piece here certainly gets reflected up and curving out. Great. So nice graph. We get to see the parabola. And now let's try and come up with the piecewise function for this. So what we're doing is we're graphing f of x. If Now in this case, there's two breakpoints, two places where the graph is very different. Those are at the x values of 2 and 4. So what I need to do is create intervals from everything up to 2, between 2 and 4, and everything above 4. So everything less than 2, everything between 2 and 4, and everything greater than 4. And again, I got to pick some of these to have the absolute, or so the equal sign, so we might as well go with the middle one. Just kind of looks prettier. I'm going to actually do the middle parabola first. The middle parabola is the region here of just the vertex. And that actually looks exactly like the parabola that we were given. So what parabola are we given? We're given negative x minus 3 squared plus 1. Now, just to see what this looks like, I'm going to draw maybe just in kind of orange here, the vertex below the y-axis or the x-axis. That orange vertex coincides with the parabola which is above. So both those pieces are going to have the same equation. The equation of that parabola is x minus 3 squared. It's shifted down 1, and it's a positive parabola. So when I try and graph x minus 3 squared minus 1, I will end up with this orange parabola, and it's only defined less than negative 2, so not in between here, and greater than 4. So from this 4 and up, and from 2 and to the left. This is going to be a little bit more of an advanced technique coming up with these piecewise functions. Give it a good shot, and we can talk about it in class. This ends the notes for absolute value functions, sections 8.1.